Okay, good morning everyone and welcome to Chemistry 101, and today we are going to continue with chapter 7, which is about atomic orbitals. And today we are going to talk about the atomic orbitals as well as electronic configuration. So first of all, we need to talk about the energies of the orbital. Now, last time I told you that the energies of the orbitals are determined mainly by the principal quantum number L, so N here gives you also the energy. So N is 1 has lower energy than N is equal to and 3 and so on. Now in hydrogen atom, there's a special case in hydrogen atom where the hydrogen atoms actually the energy is only determined by N, by the principal quantum number. So there is a special case for hydrogen that the energy is actually only determined by N only. With other atoms, it's a different story. So hydrogen here, hydrogen has actually only one electron on it. There is only one electron, one proton. And that electron exists in the first 1s orbital, okay? There's only one electron sitting in 1s orbital, and N equals 1 down in the ground state or the ground level. Ground level means the first level. Now all of these orbitals at the top, they are empty, and there is no meaning for them, of course, to have different energies. So for N equals 2, there is 2s and 2p orbitals, but they are empty, okay? And there is one electron downstairs that are not affecting these orbitals, and therefore these orbitals are degenerate in hydrogen atom. So in hydrogen atom, the 2s is equal to 2p, and the 2s and the 3s is equal to 3p equals to 3b, and so on. So this is only for hydrogen atom that the same subshells in the same level, so 2s and 2p are degenerate in hydrogen atoms, as well as 3s and 3p and 3d. Now, this story will change if you have different atoms, of course, like helium or any other atom. Now, the electronic configuration of an atom, it specifies with 3 symbols of 3 letters. So for example, when I say 1s1, the first one to the left here, it goes for the principal quantum number, which is n. So 1s is n equals 1, and 2s is refers to n equals 2, and so on. The s is referring to the angular momentum quantum number, and we have a table for that. And as you know by now, that when L is equal to 0, then that's S. When L is equal 1, that's P, and so on. And the subscript 1 at the top, that refers to the number of electrons in the orbital. So, and the number of electrons are actually depends on the type of the orbital. So we have S, P, and D, and F. And for S, the L is the quantum number is 0, here is 1, and here is 2, and here is 3, and so on. And for the number of electrons that each one occupies, the S can occupy only 2 electrons, while the P can get up to 6 electrons, and the D can get up to 10, and this one can get up to 14. And this all came from quantum mechanics, as you know. So when we distribute the electrons in electronic configuration, we have to keep this in mind. Now, the order of the filling, it goes according to the rule that you might know, that SS, PS, PS, DPS, DPS. So it goes from 1s into 2s, and then 2p, 3s, 3p, 4s, 3b, 4p, 5s, and so on. So this has something that you need to memorize, or you just memorize the song that says SS, PS, PS, DPS, DPS. So the song goes like this. So you can just memorize it easily. You say S, S, PES, PES, and then DPS, DPS. And then you put the numbers, because you know that S start with 1. So you have 1s, 2s, 3s, 4s, okay? And then 5s, and then 6s. But the P starts with 2. There is no 1P, so 2P, 3P, 4P, 5P. In any exam or any homework or an assignment you want to do, you might need to sing the songs a couple of times in order to record it. So 1s, 2s. Now the D goes from 3, so you have 3D here and then 4D here. So now you see here there's something strange going on. The 4s is actually we fill it up before the 3D according to this rule. So this all came from quantum mechanics, is that these orbitals are arranged this way. Okay, and we're going to explain some of these very soon. So as an example here, we can just throw a quick example. What is electronic configuration of, let's say, lithium? So lithium has 3 electrons on it. So if you want to fill these electrons, you fill the 1s first, and then the 2s. Okay, there are the 1s can take only 2 electrons, so 1s2, and then there's 1 electron left that goes to the 2s1. This is called electronic configuration for lithium. Electronic configuration. Okay, simple like that. Let's take another example, which is boron. Boron has 5 electrons on it, and therefore you can go with 1s, 2s. Now we need the 1s takes 2 electrons, this one 2 electrons, so there's 1 electron left that goes to the 2p orbital. So in boron we have this electronic configuration and so on. The more you practice this, of course, the better. Now, before we go into electronic configuration, why we need to understand why actually that the 2s. So here, so before I said that in the hydrogen atom, the 1s goes first, and then 2s and 2p are degenerate. That means they are having the same energy. But in atoms other than hydrogen, now we just decided that we fill the 2s first and then the 2p. That means the 2p has higher energy than the 2s. Okay, and why is that? Now this is the question that we need to answer. The answer for that is why orbitals, they have relatively different energies. That's because of 2 things. Because of something we call shielding and something we call penetration. I'm going to explain this and so on. And the idea of shielding is very important to understand concepts in chapter 8. So bear with me here when I explain the shielding effect. For shielding, basically you have a nucleus, and this nucleus is surrounded by electrons in different shells. So you have electrons in the first row, let's say, and electrons in the second row and third row and so on. It's like a party, and there's a singer or somebody who is in the middle, and there are people closing to him or her, and there are other people in the further below. Now these people or these electrons in the furthest orbital or the outer cycle actually cannot see the singer, or cannot. It's very difficult. They're trying to get them to come close to the nucleus or to this singer, but the electrons in the first shell are shielding them, are preventing them. It's like guards. Okay, so this is the shielding. Okay, so in this case we say the valence electrons or the outer electrons are shielded from the nucleus by the inner electrons or by the first row. And we're going to come to this again. That's the first reason why orbitals actually are having different energies. But the other important one is the penetration. If you look at the orbital diagram for the different orbitals, let's say 1s and 2p and 2s, you will see that they're having different curves. Now in this graph, you have the radial probability on the y-axis. This is the probability of finding the electrons in a given orbital. And you have the distance from the nucleus. Now, I want you only in this graph to focus on the 1s and the 2p orbitals. Okay, so it's going to be the red line here and the blue line. The 1s, which is the red line, it starts from 0. That means the electron does not exist in the nucleus, which is 0 distance from the nucleus. So inside the nucleus, there is no electrons. The probability jumps quickly, just few angstroms from the nucleus. It goes up and it goes down. While for the 2p, which is the blue line, okay, just focus on the blue line and red line here. The 2p goes, it's again the same thing. It's 0 at the nucleus, okay. But when you go away from, we just walk away from the nucleus a little bit, the probability increases and then decreases. But so let's think about an electron that wants to come and sit into the sit next to the nucleus like hydrogen. If these electrons want to go and to sit into these orbitals, he has a probability to be here or on the 2p and the 2s. And clearly, the probability of 1s is very high, so he goes and sits down in the 1s. Now, for the second electron, he can also go to the 1s because the 1s contains both. But for the third electron, now the third electron, the 1s is occupied. So this third electron can go to the 2s or the 2p. But watch here, the 2s here. If you look at this area here, I'm gonna zoom in. Just 1 second, please. For the third electron, now he has an option either to go into a 2s, which is the green line, or the 2p, which is the blue line. And clearly, at distances close to the nucleus, the probability of the 2s is higher than 2p. Look at this. The green line of the 2s is higher than the 2p in this area. And therefore, there is a more possibility for this third electron to exist in the 2s rather than 2p. We call this penetration. Penetration means that the 2s is penetrating more towards the nucleus than the 2p, and therefore 2s has lower energy than 2p. Okay, so to cut the story short, the 2s is lower in energy than 2p because of this penetration effect, and this actually applies to everything else. Like this is why the 3s is lower than 3p and so on. So I want to make this clear again for you that in hydrogen atom, the first level, it's called the ground level, which is the 1s. This is called the ground level or ground state. This is hydrogen atom only, okay? And the 2s and the 2p are degenerate, and the 3s and the 3p and the 3d are also degenerate. That means they have the same energy. That's only for hydrogen atom. Now, if you switch that to another atom, for all other atoms, including helium, lithium, sodium, whatever you like, the ground state is the 1s, which is the lowest in energy. But the 2s would be a little bit lower than 2p. And the 3s is the one lower than 3p, and so on. So you will get this difference in energies as the slide shows. And this is because of penetrations and shielding. And that's why you have this electronic configuration that starts with 1s and then 2s, 2p, 3s, 3p, 4s, and so on. Okay? Now, when you distribute electrons and electronic configurations, you have to keep in mind 3 rules. We have the Pauli exclusion principle, we have aufbau principle, and we have Hund's rule. Now, the Pauli exclusion principle states that no 2 electrons in an atom can have the same set of 4 quantum numbers. This is Pauli exclusion principle, and this is actually the result of that is we have only 2 electrons in the s orbital. And I'm going to explain this quickly here. Is that if you want to distribute electrons, so let's say in lithium, for example, we have 3 electrons, right? So let's call them electron 1 and then 2 and 3, okay? So the first electron will have, it's going to set in a 1s, so it's going to take n equals 1, l equals 0, and then ml equals 0, and then let's call this plus half, okay? We'll give him the plus half for ms. For the second electron, well, okay, let's give him an ID. It's like, you know, you go into the registry and to the government registry and you issue IDs for the electrons. So the government will give him 100. Well, plus half is taken, so he's going to take minus half. Now, for the third electron, I'm going to write something wrong here. What are you going to give him? 100 third? That's not possible. 101 half? This is not a correct even quantum number because ml can go from minus L to plus L, and you will be trained on how to locate wrong quantum numbers. So in that case, you must have to go into the second one. It's like car plates or car registration plates. You have to go into 2, 0, 0, half, which is a 2s orbital, okay? And this is how you do it. And this is Pauli exclusion principle. Is that no two electrons can have the same set of quantum numbers. It's impossible to have two electrons with the same ID. The result of that is that S has 2 electrons and P has 6 and so on. So that's Pauli exclusion principle. So this is what we've been talking about. I explained this already, that in atoms other than in multi-electron atoms means something other than hydrogen. You have the 1s first and then 2s and then 2p, 3s, 3p, 4s and so on. So you should memorize this. Either you memorize this graph or you memorize the song as I told you. Now, alhamdulillah, thank you. Now, for the Hund's rule, the rule says the most stable arrangement of electrons in a subshell is it's one with the greatest number of parallel spins in which unpaired. So Hund's, he likes unpaired electrons. Unpaired electrons means electrons that are all either going up or down. So for the 1s, we have one electron spinning up, one electron spinning down. That means one is plus half for ms and one is minus half. And we should pair these electrons, okay? Because they should be paired. That's Hund's rule. For the 2s is the same thing. For the 2p, now we have different possibilities here. Either we spin the two electrons in the first px, or we write it down. This is the best way to write them down. It's like all of them unpaired. We're going to practice this soon. This is called Hund's rule. Now, let's talk about, write the electronic configuration of oxygen. Oxygen has 8 electrons, and see what is possible for that. Now, for oxygen, we can start with 1s2, 2s2, and then 2p. Now, there are 8 electrons. That means we have 4 here electrons, right? Okay, so 2, 2, and 4. So we got this from the template, from the standard electronic configuration, and these numbers at the top, these are the number of electrons. The 1s only contains 2, 2s contains 2, and the 2 and the p can occupy up to 6. So we get the 4. So this is our 8 electrons. Now for Hund's rule, the 1s electrons are paired. The 2s also are paired. So these we have no problems with them. Paired means one is up, one is down, like married. Now for the 2p shell has 3 subshells, px, py, pz, as you remember. So this is 2py and 2px, 2py and 2pz. Now if you think about it, actually, you might have different scenarios for this, for these 4 electrons. You can put 1, 2, 3, 4, and this is the correct way of doing it. If you see how I'm writing this down, I say 1, 2, 3, and then I go back 4. Or you can put it like that. This is 4 electrons. Or you can put it like this. Well, there is no other way to do it. Okay, we can put it like that. Okay, or even you can put it like this. If you can play with this at home. You can do something like this. This is wrong, this is wrong, this is wrong, this is the right way to do it. Because according to Hund's rule, we should have the maximum number of unpaired electrons. So here we have 2 unpaired electrons in the top one, and in the second one we have no unpaired electrons, and the third one we have no unpaired electrons. This one looks fine, we have 2 unpaired electrons, but this is wrong, because if you are sitting, because these electrons, you know why this is wrong? Because these electrons, they have the same quantum number, and this is not allowed according to Pauli. So this is against Pauli, not against Hund's. This violates Pauli principle because they have the same quantum number. Good. So we're going to practice this, as I said. So now let's talk about also something called magnetism. You know, some materials like iron, they attract to the magnets. We call them we call them paramagnetic materials. okay, paramagnetic materials. But we have substances that are actually repelled by a magnet, and we call them diamagnetic. Now, before the quantum theory, there was no, because there, and that's another failure for classical physicists, that they didn't explain this. People didn't understand why some electrons, they are paramagnetic and some of them are diamagnetic, because they know nothing about the 1s and 2s and orbitals and all of that. This is all new in science. It's just less than 100 years old. Before that, they were thinking just the electrons are in shells rotating about the nucleus, and they didn't explain what is the cause of paramagnetic environment. According to quantum mechanics, a paramagnetic material should have unpaired electrons. So, for example, in oxygen, the one I drew, it has a 2p. Well, this is not for oxygen, but this is for another material. But you have here two unpaired electrons. This material is paramagnetic. A diamagnetic, we have all the electrons paired. Okay, paired. Yani one down, one up, one down, one up, one down. There is no unpaired electrons in diamagnetic. And without knowing about the electron configuration, it's very difficult to explain this. So, for example, if you take another example for paramagnetic, so in this case, oxygen is paramagnetic. You can watch a video on YouTube, if you like, about oxygen being paramagnetic and how it attracts to the nucleus. But let's take, for example, argon. And this is an exercise to practice electron configuration as well as deciding if it's paramagnetic or diamagnetic. So argon here, if you look at the periodic table, it has 18, 39.9. 18 is the atomic number. 39.948 is the mass number. Of course, when we need to consider electronic configuration, we look at the atomic number, which is the 18. So argon has 18 electrons on it. So if you want to do that, you're going to start with 1s. So I'm going to do it like that. SS and then PS. Let's see if this is enough. If it's not enough, then we can add more. So this is 1s, 2s, 3s, 4s, and this is 2p, 3p. Let's see. So this is going to be 1s2, 2s2, 2p6. That's 10, okay? And then 3s2, 3p6. 2 and 2 is 4, 10, 12, 18. Then there is no need for the 4s. You see, that's easy. This is called the electronic configuration for argon. In a clean way, it's 1s2, 2s2, 2p6, 3s2, 3p6. Now look at this. If I ask you if this argon is paramagnetic or diamagnetic, all of these are paired. Okay, if you can do them by yourself. But look at the last one, which is the most important. 3p has three subshells: 3px, 3py, and 3pz. And 1, 2, 3, 4, 5, 6. All of them are paired. There is no single unpaired electron in argon. Therefore, argon is diamagnetic. It does not attract to a magnet. So this is now a few examples of electronic configuration for some atoms. And as I said, it's sorry guys, are you still with me here? Everybody still with me? Can you hear me? Hello? Yes. Sorry for this technical difficulty. So so the question is, Is lithium paramagnetic or diamagnetic? Well, we cannot know before we obtain the electronic configuration. So this is the electronic configuration of lithium. It has only 3 electrons, so 1s2, 2s1. The 1s2 is paired. We have one unpaired electron in lithium sitting in a 2s orbital, and therefore lithium is paramagnetic. Paramagnetic means it has one or more electrons unpaired. Beryllium, the next one, has 4 electrons, so are paired. All of them are paired, and therefore it's diamagnetic. Okay, paired يعني كلهم one down, one up. It's يعني paired. Okay. Boron has 1 unpaired electron, and same for carbon. It has also 2 unpaired electrons, and both boron and carbon, they are paramagnetic. Boron and carbon are both paramagnetic. And it continues for the N, oxygen, fluorine, and neon. They are all paramagnetic except neon, which is all paired, and therefore it is diamagnetic. Okay. To summarize here, each shell or principal quantum numbers n contains n subshells. For example, the n equals 2, there are 2 subshells, which is 2s and 2p. For n equals 3, there is 3s, 3p, and 3d, and so on. And each subshell of quantum number L contains 2 L plus 1 orbitals, and this is good actually, this is a good rule. In each subshell, there are, in each subshell of quantum numbers L contains 2 L plus 1 orbitals. For example, if L is equal to 1, then there are 3 p orbitals, and so on. Okay, so you can calculate actually how many subshell in each L from this rule here. And there are no more electrons can be placed in each orbitals. As I said, this is Pauli's exclusion principle. This is the most important rule here. And a quick way to determine the maximum number of electrons that an atom can have on a principal level n is to use the formula 2n squared, as we said last time. So to summarize, we have 3 rules here, which is the Pauli, aufbau, and Hund's. But we didn't talk about aufbau actually. So Pauli said that no 2 electrons can have the same quantum numbers. Hund, he mentioned that we need to unpair electrons as much as we can. But aufbau, what is aufbau? Aufbau is actually this. This is aufbau. Aufbau, he is the one who said that we have to put electrons in 1s first, and then 2s and 2p, and then 3s, 3p, and so on. This is aufbau principle, which dictates the way we arrange the electrons on an atom. Now, let us jump into questions. What is the maximum number of electrons that can be present in a principal level of n equals 3? So you can apply this, you can say, I think we solved this last time. You can use the rule here. So n equals 3, that means we can use the 2n squared rule, which is 2 times 3 squared. That means 3 squared is 9. That means you have 18 electrons. You can put 18 electrons in the 3n. And to explain this, n equals 3 has a 3s, 3p, and 3d. This contains 2, and this contains 6, and this contains 10. If you add these together, you'll find them to be 18. An oxygen atom has a total of 8 electrons. What are the 4 quantum numbers for each of the 8 electrons in the ground state? Well, this question will take some, it's time consuming, but you start with writing the electronic configuration of oxygen, which was 1s2, 2s2, 2p4. And these are the electrons, the first one, second one, third one, and so on. And then you think about it. The first electron is sitting in a 1s orbital, so you give it 1, 0, 0, half. And the second one is also sitting in 1s orbital. It's going to be 1, 0, 0 minus half. And then you continue your way, defining all the IDs of the electrons. And as you will see from this example, that each electron actually has a different set of quantum numbers, according to the principle. So here, before we leave this question, I'm going to give you the one idea is that electron number 8, for example. Electron number 8 is that, if you look here, if you look the red spot on my computer, Now, you question yourself, which one is the electron number 8? Is it this one, this one, this one, or this one? Remember when we filled this, we said 1, 2, 3, and then the last one we put it down. So actually, the eighth electron, don't think it could be any one of them. No, it's not. It's this one actually. The one is pointing down. Because when we filled this, the last 4 electrons in the P, we said up, 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 and then down. So the last one we filled is the electron number 8, and therefore the N for that is 2, because it's a 2p, and the L is 1, because this is P, and ML is 1, because remember it's minus, because this is 1, 0, minus 1, so it's sitting in ML equals 1, and the last one is minus half, because it is pointing down. So please practice this at home, and also I'm going to give you questions about that. So aufbau in German means building up, and this is the aufbau principle, which is the one we talked about, is that we fill electrons according to this song, that the 1s, 2s, 3s, and this table here shows you actually all the electronic configuration for all the atoms in the periodic table, and you can tell that. Now we have, so I'm gonna stop here for a second, and I'm gonna open the door for questions if you have any before we continue. Does anybody has a question or any clarification of this lecture? No? Since you have no questions, let's talk about something that is really funny, that is really actually, let's talk about something that is really interesting. If you look at the periodic table, you have a group 1, let's say you have lithium, sodium, and potassium. So let's do the electronic configuration for lithium and sodium and potassium. Lithium is a 3, sodium is 11, potassium is 19. Yes, 19. So the electronic configuration for that is 1s2, 2s1, 3 electrons. 11, that means you have to fill 1s2, 2s2, you have to fill the 2p6, all of it, and then 3s1. If you add this, it's going to be 11. For potassium, it's 1s2, 2s2, 2p6, 3s2, 3s2, and then 3p2, and then 4s1. 2 to 10. Okay, there's something wrong here. 3p6, 4s1. It's clearly here that these 3 elements, they have the same trend in their last shell, and this is the beauty of the periodic table, is that each group, it has the same configuration in the last subshell. So 2s1, 3s1, 4s1. You will see this in all the groups. Okay, if you do it for group 2, you'll have it to 2s2, 3s2, and so on. That's the first thing we're going to learn today. The other thing is that if you notice here that the electronic configuration of potassium is actually looks the same as sodium, right? Followed by something. So actually, you can write this down as like, so potassium is, instead of doing this, you can say it's actually sodium followed up by 3s2, 3p6. Sorry, it's not sodium. It's not sodium. Sorry. Sorry, I will come up to this later on, okay? But I just want to show you that these electrons are the same. Now you can practice solving. These electronic configuration for different atoms, for whatever you like. But let us here do something for the transition metals. Let's do vanadium and let's do chromium, okay? So vanadium and chromium. So vanadium is 23. So it's 1s2, 2s2, 2p6, 3s2, 3p6. So that's your first set, which is 10, 18. You need more. So the second one is 4s2, 3d. So this is 10, 18, 20. You need three more electrons. So this is the 3d3. Okay, and this makes sense because vanadium is the third element in the transition metals. For chromium, just 1 second please. For chromium, it's 1 electron more than vanadium, so it's the same thing. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. But we have something interesting here, because this is called the valence shell, okay? And the last one here, you have 4s2 and 3d. The 3d contains 4 subshells, okay? So this one is 4s2 and this one is 1, 2, 3, 4. This is a 4s orbital. This is a 4. This is a 3d. This is also 3d. This is also 3d. 3d. So what happens here is that this is actually not the correct configuration of chromium. This electron likes to jump here to have the what we call a half stable. So this one will leave you with 4s. You have 1 electron here, and then we have 5 orbitals filled with, all of them filled with 1 electron. So instead of saying it's 4s2 3d4, the correct one is actually 4s1 3d5. This is because of a rule that says full filled, and half filled. The orbitals. If you are able to fill the orbitals completely, or half to fill them, like either 10 or 5, that will give stability to the atom, and it's better to put it that way. This actually came from the experiment. So the electronic configuration of chromium is not 4s1 3d4, but rather it's actually 4s1 3d5.